Welcome learners. In today's lecture, we are going to look into the topic of Ampere's law. Then we'll find the magnetic field equations as an application of Ampere's law that will be similar to the Biot-Savart law. Then we are going to conclude the discussion with the topic of the curl, which is going to be our third vector identity with the del operator. And then we are going to have a look at few of the numerical problems. So now what is Ampere's circuital law? The Ampere's circuital law is also known as Ampere's work law because the current is moving by doing some action or some work around a closed loop. So what's the need of the Ampere's circuital law? So we saw in the previous electrostatic section that most of the problems which were or could have been solved with Coulomb's law were easily solved using Gauss's law. So whatever equations we found with the help of the Coulomb's law that gave us the electric field intensity equations, they were easily solved when we utilized the Gauss's law in view of the electric flux density D. In the same way, most of the magnetic field intensity can be found by the Biot-Savart law, but we utilize Ampere's law because it eases our calculation, especially when dealing with integration, as Ampere's law is limited to a single closed line integral. So we can say that the Biot-Savart law resembles the Coulomb's law, not exactly, but to some extent. So the Biot-Savart law resembles the Coulomb's law, and the Ampere's law that we are going to study now is similar to the Gauss's law, where the Gauss's law was defined as a closed surface integral of electric flux density in order to find the charge. So Ampere's law is in the similar lines. Now let us look at the Ampere's law equation. So the Ampere's law states that the integral of the magnetic field intensity about any closed path is directly equal or proportional to the current enclosed by that path. This equation over here mathematically represents the Ampere's law, where we can see that the magnetic field intensity in any closed path following certain distances or traveling certain small differences by delta L is going to be equal to the current flowing through that path. We can visualize this mathematical expression of Ampere's law as such. So consider we have this closed cylinder, or we have this current carrying cylinder where current is moving inside. So as soon as the current starts to move, as per right hand thumb rule, if the current follows the direction of our thumb, we can see the magnetic field is produced in a closed path around it, as can be seen in the figure of A. Same can be seen for B. The shape of the closed loop may change, but the closed loop will remain the same. But if we come to point C, we can see that it is following a closed path in the form of a pier, but it is not entirely closed because this portion is inside the conductor, represented by these dotted lines. Hence we can say that path A and B exactly follows the Ampere's law as such that the magnetic field is completely following a closed path, but not the third or option C. It is just following half of the equation because magnetic field is not completely enclosed, rather it is closed in some of the portion and rest is inside the conductor. So this is what the Ampere's law is telling us. So we can say that for part C there is only half of the current that is making the half of the magnetic field to be generated. So what are the subscripts utilized in the equation of Ampere's law? So basically this is the current I, which we utilize our thumb for when using the right hand convention. dl is the small amount of distances that is covered by magnetic field. So we can say if this is the loop, so certain portion from this loop is dl, then here to here it is dl, and here to here, so it is a small amount of current in few sections which is moving. And then H is the magnetic field that is closed. And we say that Ampere's law is similar to Gauss's law because Gauss's law for any charge was also equal to the electric flux density closed in small surface. So these equations look alike. Now let us look at some of the applications of Ampere's law, starting again with an infinite long filament or conductor, as we saw with the Biot-Savart law. And we can see that when we apply the Ampere's law to the infinite filament, we get the same representation of the magnetic field as we got with the Biot-Savart law. And it also makes sense because both the equations or Biot-Savart law is extracted from the Ampere's law, where we had, just to recall, the infinite line. If I can redraw it on x, y, and z. So if it is going to positive infinity and negative infinity, and we suppose that the line is along this, where the current is flowing through this infinite line, if this is point 2 where we want to find the magnetic field intensity, we select a portion which was known as the differential length, and we draw an imaginary line which is showing the distance r from the origin, and this is rho. So we found that the magnetic field intensity was the same as we are getting from the Ampere's law, and mathematically we can also prove it as current is equal to dot product of a closed form of magnetic field with its differential length of the current. So if we input the integration limits, which is from 0 to 2 pi along the azimuthal plane, which why, because the magnetic field, if the current is moving in the upward direction, magnetic field will follow the a of phi axis. So once you integrate this, so h becomes h of phi into rho d of phi. This is basically your differential element dl, and then you take out the coefficients and you just integrate the d of phi, so you get the same value, and thus the equation is similar to the Biot-Savart law for an infinite long conductor. Similarly, if we have other surfaces, what is the Ampere's law, or basically the magnetic field intensity for those surfaces? So we find the magnetic field intensity of a surface current. So here we have this surface shown over here, and the current is moving in the direction horizontally to the ground or along the y-axis, as we can see. This is x, this is y, and this is z. So since the current is moving along the y-axis, we apply the right hand rule. We can see that the magnetic field is formed over here, represented by these points from 1 to 1 dash, 2 2 dash, and back to 1. So this is the magnetic field intensity. Now what is K? We saw earlier that K is basically the surface current density. So whenever we are dealing with the surface currents or current density on a surface, we represent it with K rather than the current density J. So this is K, and then we can see that the magnetic field is only appearing on the top side of the surface, not on the bottom. So our magnetic field will be just represented by half K cross product with the normal product. What is the normal? Because the normal is the effect of this field is leaving the surface along the AZ direction. So this is, or you can say that the magnetic field effect over here is normal to the surface. So that's why the equation has the unit vector normal, but remember it's a cross product, not a multiplication shown over here. So this is one representation of the magnetic field on a surface sheet. Similarly, Ampere's law can be used to find the magnetic field inside a coaxial cable. We read about the coaxial cable in previous sections, where it has an inner conductor surrounded by an outer conductor. The radius of the inner conductor is A, and the outer conductor has then two portions, the inner portion and the outer portion, where the inner portion has radius B and outer portion has radius C. So if the current is moving inside the inner conductor, the magnetic field according to right hand rule will be formed, and we can see if the current is coming out of the outer conductor, then again the magnetic field will be formed. So the image B basically shows the motion of the magnetic field in the positive phi and negative phi direction for the inner conductor, and the current coming out of the outer sphere. So this is the current coming out and this is the current entering. Then what is going to be the behavior of the magnetic field? That is shown by this seesaw motion of the phi and rho. But again, we don't want to go into the proof. We'll just utilize the magnetic field equation shown here that shows the relationship between I by 2 pi rho. So this is basically utilized if we have an infinite long conductor, and then the radiuses are given a comparison ratio, but we have to keep in mind that rho, or the radial length, should be inside these two radiuses, which is the inner conductor and the outer conductor. So this is the second part or second application of the Ampere's law in terms of coaxial cable. Third, we can find the Ampere's law for other geometries like a solenoid and toroid. So here on the left we can see we have a fully constructed solenoid, a solid material, And again, we are interested in the surface current densities represented by K along the surface. So if we are inside this region, so the magnetic field is found as such. If we go beyond this region, then the magnetic field doesn't exist. Similarly, if we turn this solenoid and make it in form of a coil, so there is no solid object, rather it's a spring and with cavity inside, the magnetic field then depends upon the number of turns and the distance d of this solenoid, which is how we find the magnetic field intensity. Similarly, finally, we can apply the Ampere's law to find the magnetic field intensity of toroids. Again, on the left, we have a solidified toroid with the radius a. So inside the toroid, we can use this equation. Outside the magnetic field, it's 0. And if the toroid is made like an electromagnetic coil or wounded around with these wires, then it can create an electromagnetic, where the equation again depends upon the number of turns of the coil and the infinite value of I divided by 2 pi rho. And all these magnetic fields are produced around the a phi because the current is moving along the z-axis. So these are some of the equations that we need to know, but rather we are not going to derive them for the magnetic field intensities as per application of Ampere's law. Now let us talk about the third vector identity that we are going to utilize, and that is known as a curl operator. So it is going to be represented as a del sign. Now what is a curl operator? But before we dive into curl operator, we need to figure out the comparison between the other del operators we have utilized. So let us first understand that what are the del operators in terms of divergence. Then we talked about gradient in the fourth chapter when we were talking about potential, and now we have the third vector identity that is associated with curl. All of them have the same del operator, but the divergence was something like the first Maxwell's equation, divergence of D, which means that if we have a charge, something is coming out of it. So this is basically divergence. Then we had a gradient of V, which was used to find the electric field intensity. So it is basically a potential, meaning something that is changing from point A to point B. So what is the change? That is represented by the gradient. And now we are having a curl of the magnetic field. So curl, basically magnetic field, will equal to the current density, and this is your second Maxwell's equation as well. So curl basically talks about circulation per unit area, something that is moving. What is circulating? Obviously the magnetic field. So now, just to give you an analogy from the book, that how the three are related. For example, if we have a lake and the water is moving as per its currents, and we say an object falls, let's say an object falls into the lake. So this is object at point A. Now if we see the object move along the same current to point B, we say that this change along the flow of the object or following the waves or the water currents is represented as gradient. And we can see there is a change in the behavior of the object as per the waves. Similarly, if this object was at point A and we see sometime it moves to this side, sometime it follows the currents in the opposite way, sometime it would come here. So this kind of motion for the object is now known as divergence. Again, the object is the same, it is placed inside the lake, but its motion is giving us the idea between the divergence and gradient. And now if the same object is moving from A to B, and after some time there is a whirlpool inside the water, so we can say it is something like this, and the object starts to revolve around certain point of axis, or it is moving or circulating, we say this behavior is nothing but the curl. So this is the representation of the curl with the analogy of object inside a water. So hopefully now you can understand the comparison between these three elements. So we can say that curl is basically giving us the rotational effect of the magnetic field produced by the current, and that current can be moving in the upward direction or the opposite direction. So coming back to curl, any vector A field's definition of curl is defined as curl of A in the normal vector. Now why we are saying it's a normal vector? Because we saw previously that whatever the object is going to move, either it will come in the downward direction or it can go in the upward direction. It's like of a spiral movement. So it can move in the upward direction or it can move in the downward direction. That's why you use the n subscript over here. So curl of any vector is represented as limiting the delta Sn tends to 0, where delta Sn is the surface, and then on the numerator you have a closed integral of line integral of a dot dl. So this defines the curl. So let us understand this equation of curl in a more simpler way. So we can say that if I have our coordinate systems x, y and z, and by any motion of current we are getting this circular magnetic field in a closed path. Let's say the magnetic field is moving in the counterclockwise direction, and at the center the magnetic field is having a value of h naught that can correspond to all the x's, hy along ay plus hx along ax and hz along az. So this is the magnetic field intensity now at the center. So this rotation is because of the, or this rotation is of the magnetic field, which we represent as curl of h, and obviously its output will be out of the surface, so it is normal. So we can say that this is along delta y and this is along delta x, and the closed path can be represented by certain points 1 2 3 and 4. So the magnetic field is now following certain line, and this line is in a closed path. Hence we can say that the magnetic field is following certain sections of the line, and this is a closed line. And since it is following certain area, and that area is delta x and delta y, so I can say this represents my curl, or the current's effect is shown as over here. Now so this corresponds to the equation of curl, where this portion is the magnetic field circulating in a closed path on a line, and delta x and y is basically represented as the surface, which is normal. And since this normal tends to 0, we can be left with just a single point over here. This means that this loop will start to shrink. So limiting delta S tending to 0 means that this object or this field may shrink to just a point, but the effect of curl or rotational effect will be there. Hence we can say that this equation here is also, or can be represented as curl of H. This ratio can be written as the current density, because we know current density is current per unit surface. Hence our final equation of the curl is equal to J, and we can see that the point form of Ampere's law is basically the equation of curl that is now equal to the current density over here, and this is known as the point form of Ampere law. This means that there should be an integral form of Ampere law. So integral form of Ampere law is, as we saw earlier, H dot d of L. So this is the integral form of Ampere's law, and this is the point form of Ampere's law, also known as the second Maxwell equation. We will look into this later on. Similarly, if these two equations can be related to a value, we can also relate the electrostatic effect we saw earlier. So this is the portion where we said that the conservative field or electric field is always equal to 0. So its point form will also be equal to 0. Hence these two equations are known as the third Maxwell equation. So, and this is generated from the effect of what we have seen with terms of the curl equation. So this is what the curl equation is, and this is how we are going to use it. Now let us see how can we find, because since the curl equation has two portions, the left hand side and the right hand side, which corresponds to the current density. So the curl of the equation for any coordinate system can be represented by finding this determinant value. So let us look at the equations of the curl. So if we are in the Cartesian coordinate system, we can utilize this equation. For the cylindrical we have this, and for the spherical we have this set of portion, but this becomes quite cumbersome. So we can go to the determinant representation of this. So whenever we are using Cartesian, we can use this form of representation for finding the left hand side of the curl equation. For cylindrical we can use such element of 1 by r or 1 by rho, sometimes radial is rho can be written, and then for the spherical we have 1 by r square sine theta. So these are the three terms that we can use to solve any problems related to curl, or basically solving the left hand side of the equation, which is this portion, and the right hand side of equation automatically comes out to be current density, or we can line integrate the Ampere's equation per unit surface, which is normal to it. Now let us look at an example to further understand how we can apply this curl to get an answer. So in this problem, we have been asked to evaluate the closed line integral of magnetic field about a rectangular path starting from P1, P2, P4 to P5, from P1 to P4, given the magnetic field intensity is such. So this is the first part. In the second part, we need to determine the quotient of the closed line integral. In the third part, we need to find the curl of this at the center of the area. Okay, so we start with the first part. Again, since it is a closed path, it means that if I draw this closed path, rectangular path, it is going to be something like this. So let us see if you want to draw the complete. No. Why? Because magnetic field intensity is along x and z, which means y is constant. So it is in the xz plane with y is equal to a constant value. What is the constant value? If you look at all the values of points P1, P2, P3 and P4, you'll see that y is constant at 3. So this means y is a constant at 3. So we only need z and x-axis to plot the 2D image. Now I can say I can start from point 1 over here as per 2, 3, 4. Then this could be point 2, this is point 3, back to point 4 and back to point 1. So this is my rectangle drawn in the xz plane, where y plane is a constant having a value of 3. Now in order to find the closed path, I need to apply the Ampere's law, because Ampere's law is saying that the current in a closed path, it gives you the closed magnetic field intensity on that path in smaller sections represented by dl. So which means I need to apply this integral to all the positions. So let us start with let us say segment by segment. So in the first segment, or in the first section, let's put it this way. So for the first segment, we are selecting path from P1 to P2. This is the path that we are selecting. So we can say path 1 is at 2, 3, 4, and we are moving towards path 2, which is 4, 3 and 4. Now, so H has been given to us. What about DL? Let us define the DL for all the paths using this image over here. So it means that for path 1 we will have certain value of DL for path 2, for path 3 and path 4. So all these paths we can see when we move from P1 to P2, we are moving along the positive x-axis. So this means that DL in the rectangular coordinate system is dx along ax unit vector plus dy along ay plus dz along a of z. So since we are only moving from P1 to P2 along or parallel to x-axis, it is only going to have a value of, or DL is only going to have a value of dx along a of x. Similarly, when we are moving from P2 to 3, we are moving downward in the negative z direction. So DL in this case will be minus d of z along a of z. For P3 to P4, we are moving in the negative x direction. So it is going to be negative d of x along a of x. And then from P4 to P1, we are moving in the positive z direction. So it is d of z along. So these are the DL values for all the paths. Now we come to the first segment or the first path. We can find the amount of current over here by H dot DL. So this is the integral. It is equal to, so the value of H is 3z along a of x minus 2x cube along a of y. Now since the value of z is the same when I move from path 1 to path 2, we can see it's 4. So we can just incorporate the value of 4. So it becomes 12ax minus 2x cube a of y. Now what is h dot dl? So this is the value of h. You multiply it with dl for path 1. So the path 1 is dx of a of x. So this and this will remain, this will cancel out because the dot product is 0. So I will have 12 d of x. So this is the h dot dl. Now I can integrate it to complete the value. So I'm going to integrate h dot dl, which means I'm going to integrate 12d of x along x-axis, so its value will be from 2 to 4, the limits. And once you solve this, the answer comes out to be 24. So this is the answer for the first path or the first segment. Let us do the same for the other segments. So let's go to the second segment, keeping in mind for the second segment the path will be negative d of z. So for the segment or second section, again we need to find h dot dl. So we can say that h is, what is h? It is 3 of z and 2x cube. So it is 3 of z along a of z minus 2x cube along a of z. So again, what can we input over here? We know from 2 to 3, or let me write it over here. This is path from 2 to 3, where the values from 2 to 3 are 434 to 431. So it is from 434 to 431. Again we can see that the value of x remains the same, so I can incorporate x over here. So it will be 3 of z along a of z minus 2 4 cube along a of z. So this then comes out to be 3 of 3 of z along a of z minus 128 along a of z. So did I put the value of h? Sorry, this is a of x. It is not a of z, it is a of x. That is along a of x. This is along a of x. This is along a of x. Okay, so this is what I am getting. Now once we have this, we multiply this with dl. So h dot dl is going to be 3z along a of x minus 128 along a of z, multiply with d of l. D of l for the second path is minus dz of a of z. So it is minus dz with a of z. Again this will be 0 and az dot az will be 1. So it is 128 d of z. Now 128 d of z, we can integrate this. Since this is along z, the value of z is from 1 to 4. This is, so as we are going from 2 to 3, so the limits will be 4 to 1. So once I integrate from 4 to 1, I'll get the answer of 384. So this is the answer which I am getting for the second part. Now let's come to the third section or segment. Here again I need to find, so here the direction is from P3 to P4, which means my values will be from 431 to 231. 431 to 231 and h dot dl. So I'll just write it immediately now. So h is going to be 3ax minus 2x cube a of z, and I have taken at z equals to 1 because z is having a common value. So this is the h value, and then we can do h dot dl, where dl is having a value of, for the third path, is minus dx So it is going to be 3ax minus 2x cube a of z multiplied with minus dx a of x. Let me check again. Minus d of x a of x. So it comes out to be, this portion will be 0. You will have a value of minus 3 d of x, and then we can integrate it as per x, which is going to be from 4 to 2. 4 to 2 because this is where we're going and this is where is starting point, and the solution comes out to be 6. So I leave the solution of segment 4th for you. I'll just write the answer. The final answer of h dot dl then comes out to be, with the limits of 1 to 4, following the same process as we did previously, is minus 48. Once we have this, the total closed path or the total H field comes out to, you add, or the total current in this scenario that corresponds to the integral H dot dl is, you add all these solutions and you will get the answer as 24 plus what is this, the second one is 384, then you have plus 6 and minus 48, it comes out to be 354 amps. So this is the amount of current being used to generate this much of magnetic field over here. So this is the solution to the first part. Coming to the second part, the second part says determine the quotient of the closed line integral and area enclosed by the path as approximated to curl of y equals to y. So we know for the second part, solution to B, we know that the curl of H of any, so here it is y, is basically equal to the Ampere's law per unit the surface area which is normal to it, and this portion can also be equal to the current density. So here we just have this data over here because we already have the current of 354. We just need to figure out what is the surface area normal. So this, since this is a rectangle, I know that the area of the rectangle, so let me write it over here, area of the rectangle is length into width, where length is the difference of x and width is the difference of y. So it comes out to be 2 and this comes out to be 3. So if you multiply it, it comes out to be 6, and your total curl in this case for the area comes out to be 59 ampere per meter square. So this is the answer that we are getting. For the final part, we need to find the curl at the center of the area. So for the third part, let us use this portion. So we need to find the curl and at the center of the area, and then we can find the determinant of it. So we can say if it is x, y, z, and the value will be partial derivative of x, partial derivative of y, partial derivative of z. What is the value of h? So h is having a value of, this is the question. So we have 3 along ax and minus 2 along a. So this is going to be 3 of z. So let me try to write it over here. So 3 of z, y will be 0 and this will be minus 2x cube. So this is minus 2x cube for z and this is 3z and center is 0. So once you solve this determinant, you get the value of 6x square plus 3ay. Now what is x square and y? So at the center the value comes out to be, this is the answer. So at the center it is going to be value of x is equal to 3. So once you solve this, this is going to be 57 ay ampere per meter square. So this is the solution that you are going to get when you find the value of the rectangle at the center, and that's the answer. So that concludes our lecture on Ampere's law and curl with few examples. I suggest that you go home and try this next drill yourself, where you have to find the vector current density, which is basically J, by using the values in the cylindrical and spherical coordinate systems. And the equations that you have to use is, you can use this determinant to find the unknowns, and that will give you the following answers, which is shown over here. And this concludes our lecture for today.